We have about 1 minute or so, so I'll give people a little bit more time to hop on. Okay, so we have a lot to cover, so we'll get started. So this week we are going to be moving from coding and hypothesis testing, which we've done. We've done some exploratory data analysis, and this week we are going to start getting into modeling. And so specifically this week, we are going to work on linear regression. So this is going to be sort of a crash course into linear regression. And while linear regression is probably not going to be appropriate in every single situation, in fact, it might not be appropriate in most situations, it's a really good starting point for modeling. And from linear regression, you can move into things like GLMs and other types of models that are a lot more robust, but have very much the same underlying structure, the same underlying ideas. So linear regression is a technique specifically for predicting continuous outcomes. So traditionally, sort of the way that we frame this is we have y on the y-axis, and that's going to be our response variable, and we have x on the x-axis, and that's going to be our predictor. So we'll talk more about that in a moment. And the goal here is that we want to be able to draw a straight line through our points so that that line fits the data in the best way possible. And so this line represents the mathematical relationship between x and y. And it's really this mathematical statistical relationship between the variables that we're interested in. So it's not going to be perfect. Not every point is going to fall exactly on the line, but we can use this line to make predictions about y given a particular value of x. So when we are thinking about what sort of input we want to put into our model, we have x and y variables. So x variables are the predictor variables, so they are independent. And these predictors can be continuous or categorical. So for example, if we're talking about how much a house is going to cost, maybe a predictor variable would be what is the size of the lot that it's built on. It could be things like country, or if we are looking at predicting somebody's income, maybe occupation would be a predictor variable. Y is the response variable, and it is dependent on the x predictors. And so y for linear regression is, going to be continuous. And some examples of some of the types of response variables, some of the types of things that we might want to try to predict are things like the price of a house, the life expectancy of a person, the income of a person, maybe the temperature of a particular water body. These are all things that we might want to predict. And so the way that we're going to step through linear regression today is we are going to start with the simplest form of regression, and we're going to move up and make things a little bit more complicated. So we'll start with our naive model. And our naive model has no predictors. It only has a response variable. Basically, with a naive model, you're trying to make a prediction with almost no information at all. And so that's what we'll start with. And then we'll talk about univariate models, where we have a single predictor variable available. And then we'll talk about multivariate models, where we have multiple predictors available, and those predictors can be independent from each other, or they can interact. Okay, so here's sort of a broad overview of univariate regression. Okay, so this is when we have our response variable y and a single predictor variable x. So this is essentially the formula that is going to be used, and we're going to talk more about what each of these values mean. So y, which is our response variable, can be predicted given this formula, where b1 is the slope. And so essentially we're saying for each unit change in x, so as x goes up by 1, how does y change? Okay, and that's going to give us our slope variable. And then we multiply that by our predictor. We add our second coefficient, which is our intercept. And the intercept says when x is at 0, what is y? And then on top of that, there's going to be some type of error. There's going to be some degree of error around that prediction. So for example, if we were to run a linear model using the LM function, and we say we want to predict y based on x, we're going to go through the syntax when we start coding. What R would return to us are these two coefficients. It would say, here's the intercept coefficient, which is 21, and here's the slope coefficient associated with x, which is 3. And so we could take those numbers, 3 and 21, and plug it into this formula. So we could say, all right, y is going to be about 3 times x plus 21, and then there's going to be some error around that prediction. So for example, when x equals 10, we can go through this formula and we can say that y is going to be about 51. So you can see that on this plot. When x equals 10, y is predicted to be about 51 plus some error. And that error is going to be normally distributed around that average prediction. So this, you can sort of picture this bell curve as almost standing upright on that line. And this says, this is the error that we expect to be associated with that along the y-axis. So these coefficients can be interpreted and they can be used to predict the value of the response variable at different values of the predictor variables. And so I'll step back for 1 second. So when we're doing linear regression, and really any type of regression, any type of modeling, it's really important that we have some quantifiable way to measure how well our model does. So we can't just look at it and say, well, it looks like that line goes through our points pretty nicely. That's probably okay. We actually need to quantify that. So in linear regression, one of the most common ways to quantify how well a model fits is by measuring the coefficient of determination. This is the R-squared value. And so this is a measure of linear association that falls between 0 and 1. And it tells you how much of the variation in y can be explained by the variation in x. And so if R is equal to 1, all of the points would fall exactly on the line. That never really happens. So the higher the R-squared value is, the closer those points are falling to the line. So for example, in this top plot, we have an R-squared value of about 0.7. So you can see they're pretty close to that line. In this plot, it's 0.4, so they're a little bit more spread out. And down here, it's 0.09. So you can see the points don't really follow that line at all. And so that's one way that you can measure, how well is this model actually fitting. Another way to measure how well your model fits is by calculating the loss function. And so the loss function is essentially saying, how well does the model fit the data, or how much information am I losing? And so different types of regression will use slightly different loss functions. Even within some types of regressions, there are different types of loss functions that you can use. But for linear regression, our loss function is going to be the sum of the squared residuals. So first of all, what is a residual? So a residual is the difference between the observed response value and the predicted response value. So for example, if we were to look at this point right here that I'm highlighting, we would say that the observed response value here is about, 75, 80 maybe. And the predicted value at that value of x is down around, say, 55. And so the difference between, 80 and 55, that is our residual. So that's basically how far off our predictions was. And so the way that we calculate our loss function is we go to every single point, we find whatever that residual is, we square that value, so we multiply it by itself, and then we find the sum or the total of all of those values. And so what that does is that gives us a quantifiable way to measure how far off our predictions are. And this is really helpful when we are using, say, 2 different predictors and we're trying to figure out which one should we actually be using. So for example, in this figure, on the top figure, we are using x to predict y, and we're saying our sum of square residuals or sum of square errors, So sometimes you'll see SSE for sum of squared errors. Sometimes you'll see SSR for sum of square residuals, but they're asking the same thing. We'll see that our loss function is about 17,000. And then we could say, well, maybe if we use Z or Z, that's going to give us a better prediction of Y. And so we run that model. Once again, we calculate our loss function, and it turns out that that's almost 500,000. Okay, so the lower the loss function, the better. This means we are losing less information and our predictions are closer to the actual value using X than using Z. And so the way that we optimize a model or choose what model we want to use is by minimizing the loss function. We're also going to be looking at multivariate regression. And we're going to go through this more in the code, but I wanted to include the slide so that if you're going back and looking at the notes, you can take a look at the slide and sort of get a better understanding of how that formula works. But for now, we're going to move on to the coding webinar. So as I said, we're going to apply different types of linear models. We are going to figure out how to navigate through model objects because that is often very confusing. We will look at extracting and interpreting coefficients and generating predictions. We'll calculate our loss function and run some model diagnostics to see if it's an appropriate model or not. And then we'll look at some model comparison techniques. So if you have any questions about that, this is a great time to put it in chat because I'm going to be taking just a second to switch over to the other window. Okay, I don't see any questions coming up. Okay. So this code is all available on Canvas. I just downloaded this, so we definitely have the exact same version. I'm using the Module 8 webinar view file. And as always, we're going to start by loading the packages that we're going to need for this code to work. So that is going to be our ECDAT, because we're going to be using our housing data, and then ggplot2 and dplyr. Oh, and I see that there's a question that's come up in chat from Josh. What is the purpose of squaring R when you're calculating the sum of squared errors? That's because sometimes residuals can be negative, right? So you can either, if your prediction is higher or lower than your actual value, in some cases you're going to have negative residuals. And so if you go to find the sum of something, those will start canceling out, right? So for example, if you have something that overestimates a value by 3 and another one that underestimates it by 2, you might think that your error is only 1 when really it's 5. So that's why we square things. So it wouldn't actually be 5, but okay, so the first thing I want to do here is just run through a simulated instance of linear regression where we have a beautiful relationship. And so it's like, this is what you would want to see. If you're running linear regression, this is what you would want it to look like. And so for now, I don't want you to focus too much on the code and the syntax as much as the numbers that come out of it. We're going to come back and talk about the syntax as we continue. So what we're going to do in this little sort of demonstration portion here, we're going to say, let's make up some data that we know has a great linear relationship. So we have a predictor. Here we are randomly generating 500 values from 0 to 10, and they're going to have uniform distribution. So in other words, across 0 to 10, you're going to have pretty much the same number of each of those. And then I'm going to create a response variable that is a function of the predictor in a linear fashion. So here we're going to say our response, our y value, is going to be equal to 3 times the predictor. So this would be eventually, hopefully, what we'll find for our slope, plus 2, which is hopefully what we'll find for our intercept. And then I'm going to give it some random error that follows a normal distribution. Okay, I'm going to put that into a data frame. And we are going to pretend down here, I'm just going to take a look at what this looks like. We're going to pretend that this data is, the data that we've been handed, and we don't realize that it's been automatically generated. This is the data that we've been given to actually run a linear model on. Okay, so we have a response and a predictor. So the first thing you should always do when you are running any type of model is you should always visualize the raw data. Never assume that you know what relationship you're going to be looking at. Always visualize it to see if that gives you insights about what type of model to use. So we'll just visualize it as a scatter plot. And very unsurprisingly, because we know that we've just generated this linear data, we would say it looks like a linear model is going to fit this data very nicely. And so we would build a model. We'll take a quick look at this piece of code at the syntax. So we use this lm function to run a linear model. We include the formula of the model. So in this case, it's going to be the response tilde the predictor. So this is always the format that's going to take. The response goes on the left-hand side of the tilde, and the predictor, whether there's one or more, go on the right-hand side. And then we say those objects or those columns can be found in the demo_data frame, because that's what we've built up here. Okay, and so if we look at what our demo model looks like, you'll see that it spits out some information, and at this point, it's fairly simple information. It tells us that this is what we tried to do, this is the model, and these are the resulting coefficients. And so it predicts that if you were to draw a perfect line through this data, that it would have an intercept of 2.055, and the slope associated with the predictor would be 2.98. And that makes sense because when we made up our data, we said that the slope would be about 3 and the intercept would be about 2, plus or minus a little bit of error. So this makes sense to us that that's exactly what we get. We can generate predictions. So we could say, okay, if we were to just use the predictor now, what is the expected value of our response? And to do that, I'm going to highlight this piece of code. There is a fantastic function called predict. We're going to go into more detail with all of this. You're going to see predict and lm over and over and over. But the way that predict works is that the first argument you give it is the model that you want to use to make the predictions. And the second argument is the data frame that contains the predictors that you want to use to make the predictions. And so we're going to use mutate. We've all used mutate now. And we're going to say we want to add a column to our demo data called predicted, and we want to fill that column in with these predictions that we're going to make. And so now we can use that extra data. If we look at demo data now, you see that we now have 3 columns. I'm just going to look at the head of demo data so we don't have to scroll all the way up. So here's the first 6 rows. So we have our original response, our predictor, and then based on the model, what our prediction would be. So at this point, the response was actually 22, and what we predicted it to be was 20.78. So we're pretty close. And so we can visualize all of those predictions as a line. And we're going to make it red just so we can see it. And so that red line represents our linear model that we've drawn through these points. Now, to run model diagnostics, we're not going to calculate R-squared or sum of standard errors or sum of squared errors or anything like that right now. We're going to wait until we're actually running some models on our own. But I did want to briefly show you some model diagnostics. And in particular, one important plot that you should always be looking at. So I'm going to show you something here, but you have to be very, very careful with it. Okay, so please pay attention. I don't want to get emails saying I tried to do this and this weird thing happened, because this is how this function works. Back in assignment 3, I think it was, we very briefly in the assignment looked at this plot function and looked how it's really flexible. You can give it different types of information and it will automatically generate different types of plots for you. And really interestingly, if you give the plot function an object that contains a model, what it will do for you is generate 4 plots of model diagnostics. We're only going to be using one of them. But when you run this line of code, it will look like nothing has happened. But down in the console, down here, it will say hit return to see next plot. And you have to click in the console and hit return. And it will scroll through the 4 plots. But importantly, you can't run any other code until you've clicked down here and you've scrolled through the plots. So you would never want to put this line of code in, an assignment or in, a piece of code that you're giving to somebody, because it requires them to stop halfway through the code, click down in the console, do something by hand, and then pick it up again. So this is just for kind of your own purposes. And so the first plot that comes up is called a residuals versus fitted plot. Let me make this a little bit bigger so you can see. And this is the only plot of these 4 that we're really going to talk about. So what this plot means is it says if you go through all of these different predictions, how far off were our residuals when it came to that prediction? So remember, we said here the predicted value was 20 and the response was 22. And so if we went to the predicted values, we would say, okay, well, they were all kind of within like plus or minus 2. And so what you want to see in this plot is it should look just like this. There should be no pattern whatsoever. There should be sort of an equal number of points above and below that red line. There shouldn't be any, there's a pattern that sometimes comes out called a shotgun blast, where all of the points on the left-hand side are really clustered around the red line, and all the points on the right-hand side are really spread out. That's really bad. That means that your model is not appropriate. So this is the type of pattern that you're looking for. Okay, so as we go through, we will, I believe, look at how to do this in ggplot, so you don't have to keep clicking through these plots. And before you run any more code, you have to click down on the console and hit enter to go through these other plots. And once you get back to the regular prompt of that little greater than sign, that means that you can continue with your code. So please be careful using that function. Okay. So Steve is asking, well, what about the error? So the error is something, let me see, scroll back through these plots if I can. Okay, there we go. So basically what we're saying is when we say, the response is going to be equal to the slope times the predictor plus the intercept, that represents the red line. And then the error is going to be that distribution of points around the line. So we'll talk a little bit about how you, it's not so much how you calculate that error as it is how you deal with it, how you sort of look at that spread and decide, is this model worth it? So we are going to be using the housing data set. So we're already familiar with that. We are putting it into an object called housing, and we're saying, go to the EC dat package and find me the housing data. And then just as a reminder of what that looks like, because I think it's been a couple weeks since we used this, we have the price that a house has sold for, and then different characteristics like the size of the lot that it was built on, the number of bedrooms, bathrooms, how many stories it has, and then a bunch of categorical yeses and nos. So does it have a driveway? Does it have a rec room? And so on. So if we wanted to use this data and say we want to predict the price of a house that we want to sell, let's start with the absolute simplest model, which is the naive model. And so the naive model assumes that we have no other information, we have no predictors, all we have is our known response variable. So in this case, this would be as if we had this whole data set, except we only had the price column, for example. And so if you only had information in your neighborhood about, the last 100 houses that sold in your neighborhood, here's how much they sold for. The best thing that you could do to make a prediction on that little information is to look at the average price, right? That's as far as you could get. And so that would be your naive model. Now, to technically write out your naive model as a linear model, the way that we do it is, again, we use this LM function for linear model. The first piece of information we give it is the formula. And here we're saying we want to predict price based on, but unfortunately we have nothing to base the price on because we're acting as if we have no predictors. And so we end up putting a 1 there, and this is called the identity, and that in this context is saying we don't have any predictors, we just want to make a prediction about price. And then the second piece of information we give it is, where is this data coming from? So it's coming from the housing data set. So if we look at the naive model, you can see that it gives us very similar information as we saw when we did our simulated data. And so it says, okay, here's the model, and here are the results. And you notice that it doesn't give us a slope coefficient because there are no predictors. So there is no slope. And so here it says, okay, if we had no other information, we would make our best guess that a house would sell for about $68,000. And if we skip ahead a few lines and we look at the average of the housing prices, that's exactly what we're seeing. It's about $68,000. I do want to point out that in model objects, when you say, show me what's in this object, naive model, it does not actually show you everything that's in that model or everything that's in that object. There are a bunch of different ways that you can interact with model objects. One of the most common ones is that you can ask for a summary of your model object. And that is going to give you a lot more information, as you can see printed out here. It'll give you information about the distribution of your residuals. It'll give you information about your estimate, also the standard error around that estimate, and then some other information that we will talk about a little bit later. Residual standard error, degrees of freedom. So there's a lot more information there. So another way that you can pull out the coefficients, remember you can look at the model object and that will tell you the coefficients. You could look at a summary of the model object, which would tell you the coefficients with a lot more detail. You can also say in the naive model object, there's a component or a piece of that object called coefficients. So up until now, whenever we see a $sign, we've thought about a data frame, right? So we'd say, oh, coefficients is a column in the naive model data frame, but that's not actually the case here. Coefficients is a component of the object called naive model. If naive model was a data frame, coefficients would be a column. But because naive model is a model, coefficients actually contains the coefficients from that model. Okay, so dealing with model objects takes some practice, but essentially it is a list. And so if you see that and you're like, we haven't really talked about lists, we haven't really, but back in module 2, I believe it is, I do have a slide about how a list is structured. And so that might give you a little bit more insight into how you sort of navigate through these model objects. So we have our prediction. We say, okay, a house is going to cost $68,000. But how well does this actually represent the data? In other words, what are our residuals, right? So for each of our houses that we know the actual price of, what if we had predicted they were $68,000? How close would we be? So there's a few different ways we can get at this information. We could say, okay, take the existing housing price and subtract that estimate. Okay, so for example here, house 505, we were about $3,400 off in our estimate, right? House 540, we were about $17,000 off in our estimate. The other way that we can pull out our residuals is, maybe I'll switch the order of these, is just like having a component called coefficients. The model object also has an component, sorry, called residuals. And so you could run that, and that would print out the same information in a slightly different looking format, but the same information is there. So here's house 541 again, and again, it's still about $17,000 off in our estimate. We can also use this really handy function called resid, and we could say, show us the residuals of the naive model. And again, that would give us the very same information. So when it comes to models, there are often multiple ways to get at the same piece of information. Whichever of these three options makes the most sense to you, feel free to use that. So if we want to calculate the loss function, remember that is the sum of squared errors or sum of squared residuals. So you can see that these three lines are going to do the very same thing. Okay, they are all going to take the sum of our residuals, right? So it even, our student even highlights that here. Here's one way that we can find residuals. Here's another way that we can find residuals. And here's another way we could find residuals. But in every case, we are taking our residuals, we're squaring them, and then we're finding the sum. And so our loss function is pretty huge. This is a lot of information that we're losing. And so naive models are really good for establishing a baseline. This is the score that we're trying to beat. We're trying to get a lower loss function than this. I think that there are a lot of instances where people put a lot of time and effort into trying to build these really fancy models and making them really complicated and, you know, trying to get this loss function down. And at the end of the day, it turns out that their loss function is only a tiny bit better than if they had just taken the average response variable. So always make sure that you kind of do this and you have a sense of, here's the number to beat, you know, how much effort does it take to significantly lower this value? Okay, any questions about naive models before we move on to univariate models? Okay, I'll keep an eye on the chat in case someone's typing. Okay, so again, naive models, we have no predictors. In a univariate model, we have one predictor. So for example, we could say, if we look at our housing data, just the first few rows, could we use our lot size as a predictor of price? Is it maybe that houses that have a bigger lot size are also more expensive? Who knows? So we're going to build a model. We'll call it Model 1. Something that's really important is there are kind of two ways of thinking about how you name models. I tend to start with my naive model often being called Model 0. And then as I try different models, this will be Model 1, Model 2, and I'll have a notebook where I have everything written down where I say, okay, Model 1, here's the, you know, the list of predictors that are used in it. Other people want to include that information in the name. So this could be like linear model based on lot size. So that could be the name of your model. That works really well when you have simple models, but as you start making them more and more complicated, it, in my mind, becomes a lot harder to kind of come up with these standardized names. So I tend to do Model 1, but it's going to be up to you. So here we're going to say, let's run a linear model. The formula that we want to give it is we're going to say we want to predict price based on our predictor lot size. And that data is going to be found in the housing data frame. Okay, so we can run that, look at that object, and it says, okay, here are the coefficients. The intercept is about 34,000, and the lot size slope is about 6.6. Okay, so we could also look at a summary of that model and have more information about those coefficients. Or we could use the Model 1 $ coefficients to just pull out the coefficient information. So the way that we're interpreting this is we're saying that the predicted price of a house is going to be the intercept. so about $34,000, plus $6.60 per 1 unit of lot size. Okay, so if we have, I think we might do this in a little bit, but let's just say, let's say that we have a lot size of 1,000. That means that our house is going to be predicted to be 34,140. I'm going to round it, plus $6.60 times each unit of lot size. So that house is predicted to be about $40,700. I should note that this data is from, I believe, the 70s or the 80s, so it might not totally represent the prices that we might be more used to now. Okay, if we want to look at our R squared, remember that value goes from 0 to 1 and tells us how much of the variability is explained by the model. The way that we can get this information, if we look at summary of model 1, we can see that it is reported down here in the bottom. As a rule of thumb, you want to use the adjusted R squared value. As you start doing multivariate models, the adjusted R squared helps to account for the fact that there are multiple predictors and multiple higher degrees of freedom. So it's a good practice just to kind of get used to pulling out that adjusted R squared. Most of the time, it's not going to make a whole lot of a difference. And so we can see in the model summary, we do have this piece down here called adjusted R squared. And so you could print out the summary and then, look for this value. The other thing you can do is you can say, show me a list of all of the components found in the summary of that model. And it'd say, oh, here's all the different components that the summary of model 1 has. And you see the very first one is called adjusted R squared. And so that means we can say, okay, take the object created by summary model 1 and show me the component in it that has this name, right, which we get from this list. And that will print out just the value of our adjusted R squared instead of us having to look at the output and try to find it. So what this is telling us is that this model where we use lot size to estimate price, that's going to explain about 29% of the variability of the response variable around its mean. Okay, so 29%. It really depends on what field of study you're in. If you are in, medicine, for example, you probably want a much larger R squared value. You really want to have most of the variability explained. But often if you're in a field of, say, social science, people are very hard to predict. And so it's possible that if you're looking at surveys of people and doing more like social science stuff, or maybe even marketing, having a model that explains, 30% of the variability might be huge. So it's very, very domain specific and question specific. Okay, so we can look at the predictions from the model object. We can do that a couple different ways. So first, let's do it this way. We have briefly seen this predict function before. We can say predict using the coefficients generated by model 1 and the data found in housing, generate a bunch of predictions. Okay, here, so we can see that house number 541 is predicted to cost about $77,000. House 542 is about $66,000, and so on. You can also get these values from the model object in a component called fitted values. So that'll give you the same information. I prefer using the predict function because as you get into more and more complicated models, this doesn't work, right? So this will only work for linear models and a couple others, whereas the predict function works for a much broader range of model types. So let's take these predictions and put them as a new column in the housing data. So we'll use mutate and we'll say, create a column called predicted M1, and in that column, add these predictions from model 1. Okay, and then I'm going to run this and then we'll take a very quick look at the code. But now you have all used ggplot many times, so you should be able to, when you download this code, kind of go through each line and see what it's doing. And so what we're doing here is we are first starting with a scatter plot of lot size versus price. We are adding our model 1 predictions as a red line. So this is what model 1 predicts. And we're adding our naive model predictions as a horizontal line, right? Because remember, it doesn't matter what the lot size is. Our naive model doesn't take that into account. Okay, so these are our two models that we could choose between right now. And sometimes you can look at this plot and say, obviously the red line is going to give us a better answer than the blue line. But if you actually want to be able to defend that decision and quantify it, you would want to do something like the loss function. So remember, the number to beat, our loss function from our naive model, is this huge number. And if we calculate the sum of squared residuals for module 1, so again, this is one of the ways that we can pull out our residuals, we can see that this number is much lower. It's still huge, but it is much lower. Okay, and if you wanted to look at that residuals versus fitted, you could do that using plot. I'm not going to run that again. And then we could say, okay, so model 1, we said, can we use lot size as a predictor of price? So this is what we've already run. But maybe we'll say, well, instead of using lot size, could we use the number of bedrooms as a predictor of price? So let's do model 2. And in model 2, we replace lot size with bedrooms. So it's still a univariate model. There's still only one predictor. And rather than looking at a plot or generating predictions, let's just very quickly assess and compare these models using loss function and adjusted R squared. So model 1, this was our loss function. This is the number to beat. Model 2, I'm using a different method of pulling out the residuals, just demonstrating that you can do it lots of different ways. Model 2, you see that our loss function has actually gone way back up, not quite as bad as the naive model, but definitely it's not doing well. Okay, so that would be our first sign that our lot size model is way better than our bedrooms model. But you could look at the adjusted R squared. It's always good to have multiple pieces of evidence as to why you rejected one model and went with another one. So our R squared for model 1, it explained about 29% of the variability. Model 2 only explained about 13% of the variability. Okay, so here's two reasons why we could say, you know, if we're doing a univariate model, lot size is a better predictor than bedrooms. Okay, any questions about univariate models? Okay, I'll give you a moment to type. I'm also desperately trying not to sneeze. Steve says, would you do that for all predictors? You could. That could be one way of approaching the problem. You could say, I really want to stick with a univariate model. I'm going to do every single predictor and compare it. You could do that. Instead, we're going to talk about multivariate models and then take a closer look at, you know, what if we're using several predictors instead of one. So there are different ways of thinking about this. You know, you could say, well, I could do a whole bunch of univariate models and figure out which predictors are best. But that's not always a good way to go because it's very possible and often very likely that predictors are going to be interacting in certain ways. Or, you know, for example, maybe bedrooms doesn't give you any information until you consider bedrooms and bathrooms together. And then all of a sudden it says, oh, here, this actually generates really good predictions. So while there's nothing wrong with running a whole bunch of univariate models just to get a sense of your data, that's fine. But don't use a univariate model as a way of saying, well, bedrooms clearly doesn't matter. we're going to throw it out and never come back to it and never consider it again. Okay, so let's get into multivariate models. So let's say, for example, that we think that in addition to lot size, we think that the size of the lot that the house is built on, plus the number of stories it has, those two pieces of information together might be a really good way of predicting how much a house is going to cost, right? Because it's very possible you have a very small lot, but a really tall house that's going to sell for a lot more than possibly a larger lot size, but a one-story house, or vice versa. And so let's say, how does lot size and stories actually work together? So as you can see, the only thing that changes here is the formula that we're using. So instead of price being predicted using lot size, we're going to use lot size and stories. So we use the plus to say that we want to use both of these predictors together. So this is not adding lot size plus stories, right? So if your lot size is 1,000 and you have a 2-story house, this is not saying that that value is, 1,000 plus 2. It's saying that the predictor variables are both going to be considered independently. And if we look at our Model 3 object, you can see that it doesn't get a whole lot more complicated, but we do get one more coefficient estimated. So we have our intercept, and then we have the slope associated with lot size and the slope associated with stories. If we look at a summary, you see we have more information because now we have 3 parameters we're looking at. And we can still use that $ coefficients to say, just pull out the coefficients from the model. So the way that we can interpret this is this tells us that the predicted price of the house is going to be about $15,000 plus $6.20 per 1 unit of lot size, plus about $11,600 per story. So we could use that to make predictions. We could say, without using predict, just using the formula and the numbers themselves, we could say if we have a 2-story house with a lot size of 5,500, how much do we think that would sell for based on this model? So it is going to be our intercept, 15,000, plus 2 stories times 11,600 per story, plus a lot size of 5,500 times about $6.21 per unit of lot size. So we would think that that house should probably sell for about $72,500. Now, when you are trying to, decide how much you want to sell your house for, you don't necessarily want to say, okay, well, it's definitely going to be, exactly $72,500, and we're not going to take a penny less. We won't ask for any more. It's important to have a sense of the confidence intervals around these coefficients. And here I say I've typed confidence intervals for these intervals. It's actually confidence intervals for these coefficients. Okay, so here are the coefficients again. If we want to know what are the 95% confidence intervals around these coefficients, how sure are we can use a function called confint. And we could say, show us the confidence intervals around model 3. Okay, so this would tell us that, while our estimated intercept is about 15,000, realistically, if we're looking at 95 confidence intervals, it's somewhere between like $9,600 and about $20,000. Okay, our lot size here, we're saying it's about $6.21 per unit lot size. But if we're looking in these confidence intervals, the 95% intervals tell us that's actually somewhere between $5.40 and like $6.99. So looking at these confidence intervals can give you a better idea of how certain you should be about your prediction. And these are always good things to report on. So let's actually generate some predictions. So we'll do the very same piece of code we've seen before. We're going to create a column called predicted M3. Remember, we didn't even bother doing one for M2 because the model was terrible, so we just moved on. And we are going to fill that column in with predictions based on model 3. So if we look at the head of housing now, look at the first 3 rows, we can see that the actual price of house number 1 was 42,000. Model 1 predicted it was about 72,000. Model 3 predicted it was about 74,000. So let's put all of these models or all of these estimates together. So as we are adding predictors, it becomes increasingly hard to actually visualize our model, right? Because here, not only is there going to be a slightly different line, based on our red line is our lot size model, but our green line is the specific line for that number of stories. So for example, I'm gonna make this a little bit bigger to see. We could say if we have a 1-story house with a lot size of about 8,000, we would predict that it's somewhere around, I don't know, $75,000, right? Roughly. But if we have a 3-story house with an 8,000 lot size, we're predicting it's about $100,000. We have a 4-story house, it's even a little bit higher, maybe 110. Okay, so as we start adding dimensions, it becomes much harder to actually visualize this. So we can return to calculating our loss function. Remember, model 1 so far has been the lowest loss function, and that was this very large number. And we can see that model 3 has improved. We have minimized or at least lessened our loss function. So another thing that you can do to compare models, and I believe Kristen's going to be talking a little bit more about this next week, but you can compare models using this value. I can't pronounce this. I don't even try. I just embarrass myself. But it's known as the AIC. And so you can use
these ACCI's information criterion.
That is the one. So you can use this value to compare models. Now there's one very important rule about when you can and cannot use AIC. You can only use AIC if your models are nested. So nested kind of has 2 parts to it. We're really going to focus on one of them here. Nested means that your parameters in model A are a subset of your parameters in model B. Parameters being things like your predictor variables in this instance. So if you are uncertain, we could use this line of code, which we're not really going to get into what all of this means. This is returning to some base R, which we don't have time to cover. But this is a good piece of code to sort of jot down on a cheat sheet. We could say model 3, what are our parameters? Okay, our parameters are lot size and stories. Model 2, our parameters are bedrooms. So bedrooms is not a subset of lot size plus stories. Therefore, model 2 and model 3 are not nested, and you can't use AIC to compare them. Now, what's really dangerous is that R will still let you use AIC. So if you tried to use AIC to compare model 2 and model 3, it would give you a number, and the number would be completely meaningless because you can't use AIC to compare those models. So please be very careful. If we looked at model 3 compared to model 1, we can now see that lot size is a subset of lot size plus stories. So in other words, these 2 models are nested, and we can actually use AIC to compare model 3 and model 1. The other thing that you have to make sure of when you're doing AIC, and it's not a problem here because we don't have any missing data, but if you're working with a data set that has a lot of missing values, just know that if you try to include those in a model and say you're missing a bunch of the stories, right? You're missing information about stories, it's going to drop those points automatically. And so as soon as the data being used in one model is different than the data being used in another model, it is also no longer nested. Okay, so those are the 2 things. Have to use the same data, and they have to have parameters or a subset of the other model. So we have established model 3 and model 1 are nested. we can use the AIC function to compare those two models. And what we can do with this resulting information is we can look at those AIC values and determine that the lower value of AIC is the model that fits relatively better. So there's a general rule of thumb that the AIC value has to be at least 3 different. So if this one was 12,380 and the other one was 12,381, they're not different. You know, one doesn't fit better than the other. So you have to have a difference of at least 3. So this is another way that you could say, you know, not only is the SSE better, but also AIC is telling us that model 3 is better. So that could be another way of defending your model selection. So now let's talk about interactions. At this point, we have only talked about multivariate models in the sense that we can add more than one predictor. So we had lot size and stories. But what if now we say, we actually think that lot size and whether or not it has a driveway is really what's going to be important. So we're going to be introducing kind of 2 new concepts here in one. The first is that instead of using a plus sign here, you'll notice that we use an asterisk. And that means that in addition to looking at how lot size influences price and how driveway influences price, we also want to look at the influence of how lot size and driveway together interacting affect the price. So we're actually coming up with 3 coefficients, 3 different slopes, plus our intercept. So we look at model 4, and you can see we have our intercept, then we have our coefficient related to lot size, and then we have 2 others. So the other thing that we're introducing here is that this is the first time that we are using a categorical predictor, right? Before it's always been continuous or more or less numeric. In this case, driveway is either yes or no. And so what this model will tell us is that if the driveway is equal to yes, this is how much you add, or in this case, subtract from that house price. And if the driveway is equal to yes, this is how much that changes the slope of the lot size. Okay, so we can use this to calculate some predictions. So for example, we could say, how much would a house cost if it has a lot size of 5,000 and it has no driveway? So it's going to be the intercept plus the lot size times the slope associated with lot size. So that house is about $52,000. It has no driveway, so we completely ignore this and this coefficient, right? Because this is only if the driveway is equal to yes. If we have the very same house on the same lot size, but it does have a driveway, then we say, okay, we take that intercept. We have 5,000 lot size multiplied by our lot size slope. Now that we do have a driveway, it's telling us that it's actually worth about $922 less, but driveway and lot size interact with each other. And so having a driveway means that for each unit of lot size, you get an extra $3.47. So when we run all of that, we see that the same house on the same lot size with the driveway is about $68,000. So adding that driveway gave us, a bit of a higher price. I see chat lighting up. Okay, Nathan is asking, is there a way to choose between driveway yes and driveway no as the one that's being shown in the model summary? Very good question. So the way that it does it is alphabetically. So if you have yes and no, it's always going to show you yes. But this is known as, sometimes you'll hear about this order being called contrast. And so you are able to go in and reset that and see what the other contrasts are. When there's only two options, it doesn't really matter. But if you have 4 or 5 options, it can be much more complicated, and you have to go through and consider what is it actually being compared to. So, for example, if you had, if driveway was A, B, C, or D, then your baseline would be A, and then it would say, okay, driveway B, here's what you would have to add. Driveway C, here's what you'd have to add, and so on. So yes, there are ways to get around that, but not something that we will have time to get into today. Steve is asking, why is there a higher price? Because driveway yes is negative. So driveway yes will subtract about $1,000. However, having a driveway means that your lot size is worth more per unit. In this case, this is what our model is telling us. So yeah, you lose $1,000, but for every unit of lot size, you also gain $3.50. And here, because our lot size is 5,000, that not only negates losing that $1,000, but it actually adds to the total because it adds about $17,000. Okay. So if it moves from driveway yes to driveway no, it's a negative coefficient, so the price decreases. Correct. Yeah, so moving from no driveway to a driveway by itself will reduce the price, but it will increase the value of the lot size. So overall, things go up. And these are really important questions to think about, because sometimes you can, you're always going to get coefficients estimated. But sometimes it is really important to take a step back and say, does this actually make sense? It's very easy to come up with lots of coefficients with models that look really good, but then when you take a closer look at them, you say, well, this predictor makes no sense. There's some really famous examples out there of correlations that make no sense. So it's something like the number of Nick Cage movies that comes out versus like how many people die of drowning, I think is one of them. And it has a beautiful relationship. But of course, that doesn't make any sense. There's no way that one causes the other. And so it is really important to not just look at those coefficients and take them for granted, but like think about what they're saying and think about, does that make sense to your question and to your system? Okay, so we can, I see one more chat question coming up. Unless you're watching a Nick Cage movie at the beach, that is possible. Maybe that is really what's driving that pattern. Okay, so let's look at multiple interactions. As you can see, this is a very short section. This is just a common question that I get saying, what if you want multiple interactions? There are lots of different ways that you can specify what predictors you want to interact and what predictors you don't want to interact. There's a lot online about how to write these up. So we can't go through every single instance, but for example, if we were to say lot size plus stories interacting with driveway, you could see from model 5 that you now have a slope for lot size, a slope for stories, a value if the driveway is equal to yes, and then if there's a driveway, how does that change the value of lot size, and how does it change the value of stories? So you can make this much more complicated. So for example, here a driveway reduces the predicted price by about $8,400, but it increases the worth of each unit of lot size by $3.60, and it increases the worth of each story by about $2,500. Okay, so you can make these models much more complicated, even using a simple linear model. So at this point, what we've done is we've kind of moved up. We've gone from naive model with no predictors to univariate with a single predictor, to multivariate with 2 predictors, to multivariate with 2 predictors and an interaction, and now multivariate with 3 predictors with interactions between 2 of them. And so we've very much gone from like simplest to most complex. There there's different schools of thought as to how to build models and what's the right way. It's something that takes experience and talking to people and reading about things to see, how should it be done in your domain. But the opposite thing we could do here is we could start by putting every single predictor we have into the model to build a full model and then see if we can reduce it down to a simple model rather than going from simple to complex. So if we look at all of the columns in housing right now, and we say we want to use all of the predictors, one thing we want to do is make sure that we get rid of these two columns called predicted M1 and predicted M3, right? Because these are not predictors that we want to use. These are predictions from old models. So we will first start by removing the columns that start with the word predicted. So we'll use the select function and the minus, but we'll introduce just a really handy, fairly simple to use select helper. And so here you are reading it as take the housing data set and from it select all the columns except the ones that start with the word predicted. So that's kind of handy. And that's one of the reasons that if you are adding columns of predicted values, you should always name them in a way that allows you to take them out very simply later on. Okay, so now if we looked at the names of housing, you would see that those are gone. We're back to just the predictors and the response variable. And so we can now build a full model. So to build a full model, you'll notice that the function pretty much stays the same. And the only thing that's different is here we're saying predict the price based on, and by putting a period there, we're saying base it on every other column in the data frame. Okay, so predict price based on everything else. Okay, and use the data found in the data housing or the housing data frame. Okay, so if we looked at full model, you can see now we have lots of different coefficients. I should note that this does not include interactions. We're just going to stick to independent predictors for right now doing the full model. And so you see that each of those variables now gets an associated slope coefficient, or in the case of categorical variables like driveway, yes, we say, this is how much we add if it has a driveway, this is how much we add if it has a rec room, this is how much we add if it has a full basement, and so on. If you are ever looking at a model and you're like, I can't remember what full model actually was, you can look at the component called call, and that will say, here's what you actually typed out to build that model. So that can be helpful. We can use this piece of code, which we saw back when we were talking about AIC, to say, what are all of the terms? And that will actually write all of those out, saying, in the formula, this dot actually gets translated to all of this. Those are all of the other columns. We can look at a summary of the full model. Immediately just looking at adjusted R squared, it's gone up to about 66%. We have lots of information here about all of the different variables, and we're going to talk more about this in a moment. We could pull out just the coefficients. We could use that confident function that we've already seen to look at the confidence intervals around those functions or around those coefficients, right? So for example, you see, for example, lot size was estimated to be $3.55 per unit lot size, but in terms of the confidence around that, it's really from about $2.85 to about $4.23. And we could use all of that information to make predictions. So we'll add a column called predicted FM for full model, and we'll say, use the full model to make predictions based on the data we see in housing. If we look at the first few rows, we can see we now have those predictions here. Okay, so I think before this, our best model, I believe, was model 3. And that was our loss function there. It's a large number starting with 221. Our full model loss function, we can see has dropped quite a bit. So simply from the perspective of loss function, we would say this model is much better. Now, you never want to base your model selection on a single value. Loss function is very helpful, but it's not the end all. It's not the only way to choose. So we could say, well, let's make sure that these are nested, right? So model 3 had lot size plus stories. The full model had all of this. And we can see that both lot size and stories are found in this full model. And there's nothing in model 3 that isn't found in the full model. So these are nested. So we could use AIC to compare those. Right, and so the AIC has gone from 12,380 down to 12,094. So that's another piece of evidence that would say this full model is much better than our model 3. And before we get into how to use this to predict a value of a very particular house, I'm just going to check the chat because I see that it has been lighting up. Okay. Nathan says, can you adjust the confidence interval to a different level of confidence? Yes, you can. I believe that has to do with the confint function. Yeah, so in confint, you can set the level. By default, it's 0.95. But for example, we could say, what is the confint where the level is 0.09, or sorry, 0.9? Okay, and that would update those values. So you can set the confidence intervals using this level argument, but by default, it's 0.95. And Ali is asking, what is the parameter used for terms? It says 3. Okay, so I'm not going to get too deep into this, but this is called indexing, and it is a way of exploring a particular component of an object. So if we were to just look at model 3 terms, this is actually what model 3 terms contains. It contains all of this stuff. I'm not going to get into how that's structured because it's structured in a very complicated way. However, by adding this square bracket 3 square bracket, you're saying that this is the piece of that information that you're looking for, and that's where that lot size plus stories is actually stored behind the scenes in this much more complicated object type that we have not looked at. So it doesn't have to do with the model itself. It has to do with how you explore the model object. And Sue says, how would you know to do that? You wouldn't. To find that, I had to Google it and test some things out and figure it all out. So I wanted to give you that piece of code to say, okay, I figured it out. Here's how you get that information. But that's the kind of thing that you would spend quite a bit of time trying to Google and trying to explore. You might say, okay, what components are found in model 3 terms? And it would say, nope, you can't do that. You could look at the structure of model 3 terms and be like, okay, here's the structure. And then it's really a matter of like experience and practice and going through all of this. The better way to do this is to go to Google and say, how do I find what terms are in my model? And somebody will say, this is how you do it. Here's the specific piece that you have to look at. Okay, so given this full model, let's just look at the coefficients again. Full model coefficients. Okay, so here's all of our coefficients. And so what if we have a house and we're trying to figure out how much we want to sell it for? It has a lot size of 5,500, 3 bedrooms, 2 bathrooms, 2 stories. It has a driveway, a full basement, and a place to park your car. And it doesn't have any of these other things, air conditioning, rec room, all of that kind of stuff. So what we could do is write out that whole mathematical formula and say, okay, it's going to be minus $4,000 plus $3.54 times 5,500 plus $1,800 per bedroom. And we could go through and do that. But as you probably already can expect, that's a huge pain to go through and do that by hand every time. So I want to show you just a quick kind of shortcut to do that. What you can do is you can create a new data frame. We'll call it My House because it represents the house you're trying to sell. And we have seen this data frame function before back in module 2, but we haven't used it a whole lot. This is a way that you can build your own data frame from scratch, where we say we have a column called lot size. It contains 5,500. We have a column called bedrooms, which contains the value 3, and so on. And so you put all the information about the house that you're trying to sell with all of the predictors that are found in your full model. It gives you this one row data frame called My House. And then you can use the predict function to say, based on the coefficients found in full model and the data found in the My House data frame, generate a prediction. Okay, and so you could use that to say, okay, this house that I'm trying to sell is probably going to be about $79,000. Okay, so this is a really good method, and it stops you from having to actually write out all the math and reduces the mistakes made by rounding numbers or by mistyping numbers. So this is a way I would suggest you try sometime. And then let's take one more step and let's look again at the summary of our full model. And let's take a look at these p-values associated with these coefficients. Okay, so when we're looking at all of these slopes, we're basically thinking, okay, do we actually need all of these predictors to be in our model? Because remember, every single time we have to estimate a coefficient, it means that we're going to be plus or minus a little bit more in another way, right? So if you're only estimating one number, then you only have one set of confidence intervals to worry about. If you are estimating two numbers, then suddenly there's two different ways that you could be wrong. Here we're estimating, I don't know, 10 or so numbers. So there's going to be 10 ways that you could be plus or minus. And so estimating all these extra coefficients, sometimes you'll hear people say it's expensive to estimate all these parameters of a model. And so what we might want to do is look at these and say, do we actually want to make an estimate for all of these? And the one that stands out for me here is bedrooms. Right, and that's because all of these other p-values are significant. So they're saying, this is contributing to the model. This is significantly different than it not contributing to the model. And in terms of bedrooms, we're saying, well, it's not really. If our alpha is 0.05, this is 0.08. Bedrooms is not significant here. And so maybe what we do is say, let's try dropping bedrooms from the model and see if the model's any better. And so what you could do is you could, let's see, I'm going to make this smaller again so we can see. What you could do is you could say, okay, I want my, have something called my smaller model. I want that to be a linear model of price versus, I don't remember them all now, lot size plus driveway, on and on and on, type them all out except for bedrooms. But that is going to be really hard if you have a ton of predictors. So what we can do instead is we can say we want to take the full model and we want to update it. So we just change one piece. So we say we use the update function and we say we want to update the full model. And this is how we want to update it. So on the left-hand side of the tilde, the squiggly mark, we have a dot. We want exactly the same response variable. And on the right-hand side of the tilde, we have a dot saying all of the predictor variables that are in the full model minus bedrooms. So we just want to drop that one single predictor. Okay, and so now if we were to look at a summary of our smaller model, you would see that now bedrooms is not being included as a predictor. Okay, and so this would be a good instance to say, okay, well, did it make a difference? Should I have done that? Can I defend this? So for example, our full model loss function was this very large number, starts with 127. How does that compare to our smaller model? And our smaller model is actually slightly higher. So maybe we would look at that and say, I don't know, they're pretty close to being the same. You can think of, the smaller model is a little bit less expensive because we have one less parameter to estimate. But maybe we really feel strongly that in our domain of knowledge, we know that bedrooms should influence things. So maybe we want to leave it in the full model. And, when we're presenting this, make a note saying this wasn't actually significant, but taking it out didn't make a big difference. So we made the decision to leave it in there. But you could also use AIC. And here again, full model is 12,094, small model 12,095. They're not at least 3 different. So AIC is telling us nothing at all, except you can see the full model degrees of freedom is 13. Essentially, we are trying to estimate 13 different things. And our small model, we're only estimating 12 different things. So again, maybe that's enough to justify picking the smaller model. And yeah, there isn't really a solid final answer here. This is just sort of an overview of how do you go through this process? How do you think about which model you should select? How do you defend it? There is no one right answer or one right way. It's very domain specific and it's very kind of experience based. So my best advice to you is if you are running models, make sure that you're always looking at things like loss functions and AICs and residual plots and R-squared values and common sense, and making a note of why you think one model is better than the other and what evidence you have for that. Because it's not just about which one comes out mathematically nicer, it's also about which one's going to be more useful to actually answer the question that you're trying to answer. Okay, so I will stop there and open it up to questions. And while you have a moment to type your questions, I'll just note that the assignment this week is not on Vocarium. So this week, the way it works is you will go into Canvas, click on the assignment, and it's a series of multiple choice and multiple choice style questions. But you will have to interpret things and probably write a little bit of code on your own machine to figure out what those answers are. Okay, so it's kind of one step back. You're writing your own code, but you're answering the multiple choice questions. Okay, so any questions? Okay, so Nathan is asking, is there a break next week? I am 90% sure there is.
Yes, there is.
Okay.
So that
Yes,
gives
so next
everybody some time to catch up if you still need to catch up.
Yeah. And then question, could you please shortly explain AIC? Essentially, I won't explain the math behind AIC because there just isn't enough time. But AIC is a method of quantifying which model fits better using a particular formula. Okay, so when we're talking about loss function, we're talking about R-squared, and we're talking about AIC, we're using them for very similar purposes. We're saying either how well does this model fit or which of these models fits better, but AIC, formulates that in a different way than other methods. So there is tons of resources online about AIC and how it works kind of behind the scenes, but we just want to make sure that you know the function that you have to use and you have an idea of when you can and can't use it. Okay, and now on the question board, I note that people are catching up. Next week is a perfect time to catch up. If you find yourself behind on any of the assignments, you can submit a ticket to me. Just say, I'm behind on my assignments. I'm going to try to catch up over the break week. Let me know, and we're happy to take a look at those assignments after the deadlines that have gone by. Okay. Okay, well, if there are no other questions, we will leave it at that, a whole 6 minutes to spare. And otherwise, we'll see you in 2 weeks, and we'll be learning about logistic regression. So it's just another type of modeling. Oh, sorry, there's one more question. How much is this module dependent on the previous? Seems like an entirely separate module and can get the assignment done for this right away without knowledge of 5 and 6. Yeah, you probably can. But in sort of the real world scenario, when someone hands you a bunch of data and says, build me a model, you can't start by building a model. You have to start by exploring the data, doing exploratory data analysis, plotting out a bunch of things, building some summary tables, figuring out what the question actually is, looking at things like, are these data normally distributed? So in the real world, you would have to do all of the things that we've talked about in other modules. Here we're saying, start with the data, assume that it's already cleaned and ready to go, and just focus on that modeling point. Okay. So that's everything. So we will see everyone in 2 weeks. Thanks so much for joining us today, and feel free to reach out at any time. Okay. Bye.